Hello everyone, welcome to another video on the Has Motion YouTube channel. My name is Sharath Nandan. I'm currently a biomechanical engineering student at Queen's University, and I'm also working my co-op placement here at Has Motion. You may recognize my voice from some of the tutorial videos on this channel. Last week, I was given the opportunity to present my research study at the Ontario Biomechanics Conference. Today, I'll be delivering the same presentation in video format to showcase this research which made use of our software. So without further ado, here's my study titled Assessing Different Kinematic Methods of Structuring Gate. I will be delivering this in the form of an online presentation today. So let's begin by introducing what we mean by structuring gait cycles. In simpler terms, this just means breaking down a person's walking movement into repeatable chunks or cycles. To do this, we use events, which are identifiable moments in walking movement. Examples of these events are heel strike, which is to signify when the participant's foot makes contact with the ground, and toe off, which is when the foot leaves the ground. A full gait cycle is defined as a period of time between two of the same events on the same foot, like left heel strike to left heel strike or right toe off to right toe off. This full gait cycle can be even further broken down into the stance and swing phases. So by breaking down movement into these cycles, we can better analyze and compare biomechanics across time and between individuals and create varying gait measures. So right now, the gold standard for detecting these gait events is using kinetic data. Essentially, what this means is identifying contact on and contact off events by placing thresholds on ground reaction force signals. These are usually measured by force plates or instrumented treadmills. This is to detect exactly when the foot hits or leaves the ground. But this equipment is expensive and not always readily available to all labs, especially in field-based studies or markerless motion capture systems. And that's why researchers have worked to develop algorithms contributing to kinematic-based methods instead. This is to try and identify these same events using motion features rather than these force thresholds. So this includes joint positions, velocities, accelerations, and other different measures. So the question I asked in this research was, can these kinematic methods reliably structure biomechanical waveforms in the gait cycle? This matters because many gait measures are averaged across the gait cycle, and if the cycles aren't aligned properly, this could lead to these measures being misaligned or and producing misleading reports. So, what does it mean for a method to be reliable? Well, reliability in this case means that the kinematic method used to structure gait cycles is able to consistently report cycle durations that are comparable to the kinetic-based methods. We're focused on comparing the cycle durations rather than exact timing of the events that are used to split up the gait cycles. This is because the events that are found for each kinematic method could vary and don't rely on the same waveforms and algorithms as the kinetic-based methods. So the space between each dash is the cycle duration here in this diagram. And it shows three cycles using the kinetic baseline method, for example. So this diagram can help us understand what can be considered a reliable and unreliable method. Now, if we move along, we can see that this blue line represents a method that would be considered statistically similar to the baseline. The cycle durations seem to be around the same length, as you can see, but the actual events of the placement of the events has been shifted. We can attribute this to the possibility that the method is structuring using a different event than the kinetic-based methods. Now, if we move along again, we can view this red line, which represents a method that is dissimilar. As you can see, some of the events overlap with the baseline, such as here and here, but the cycle durations vary a lot. And this can be an indication that the method is unreliable. So the Fukuchi et al. Dataset published in 2018 was used for this investigation, and this dataset included walking data from 42 healthy adult participants. This was also, so of that 42, it was broken down into 24 younger and 18 older adults. Only left side treadmill data was used, and each participant had 5 to 8 trials of increasing speeds. Kinetic data was also collected using an instrumented treadmill, which provided the baseline. So Visual 3D's command pipeline allowed the creation of these events and defining of the cycles using the varying kinematic algorithms. So using the literature, I was able to actually create pipelines uh, to apply these kinematic methods and actually create cycles using them. So in total, we compared 11 different kinematic methods, and the first nine came from previous literature and research and used kinematic data to identify heel strikes and toe offs. The last two use alternative events, like when the hip surpasses the heel or when the knee reaches maximum flexion, to see if these points could also define consistent gait cycles. So to compare each method's cycle duration against the kinetic-based methods, we used a linear mixed model, or LMM. In this model, the cycle duration was the dependent variable. The method was the fixed effect or independent variable. And finally, the participants and trial were the nested random effects. This was to allow for comparison even despite walking differences between the participants and within their own trial. The diagram here shows this hierarchy and how this model evaluates our data. We want to answer the question of, does method X produce longer or shorter cycle durations than the baseline method, regardless of individual participant differences? So before we take a look at the statistical results, let's visualize the raw distribution of the cycle durations for one of these kinematic methods, the LHS foot position method. This was compared to the L-on kinetic baseline. This type of visualization gives us a first impression of if they look similar or not. In this case, the shapes and spreads of the distribution look quite close, and this suggests that this method might structure cycles similarly to the baselines. But we still need statistical analysis to confirm this. However, keep in mind that this plot here does not account for participant variability and repeated trials. So that's where this next step becomes important. So now let's look at these results from the linear mixed model, which does account for participant differences and trial-to-trial variability. This graph shows the differences in average cycle duration for the same LHS foot position method compared to the kinetic baseline. The red dotted line represents zero difference, or in other words, a perfect match to the baseline. If a method's point or confidence interval interlaps with this zero baseline, which here it's happening here, we say that there is no significant statistical difference between them, and the method is reliable and produces cycles of similar length to the gold standard. So as you can see, these are seconds removed from the average zero difference, and these are seconds added. So if the method produces consistently longer durations, it would be in this area, and shorter would be here. Now, if we expand the same plot to show all the methods, we can highlight the following three: the LHS foot position method, the LTO foot position method, and then the max knee angle or peak knee flexion method. All three of these show overlap with the zero line, as you can see, and that means they're not significantly different. This tells us that these methods can structure cycles consistently compared to the kinetic methods. Now, if we look at the others, many of the remaining ones have a asterisk over them. These methods indicate that this asterisk indicates that these methods are significantly different from the baseline using the Bonferroni corrected p-value. So why is this important? These methods methods with an asterisk may miss key features of the gait cycle or be more sensitive to the variability in walking speed or limb movement. So for example, some methods detect heel strike based on velocity reversals and limb accelerations. This may not correspond well to the actual foot-ground reaction moment due to the high amount of noise in these signals. Others might use the vertical excursions of a segment, and these can vary more in between individuals. In these cases, even the small differences in timing can add up and lead to longer or shorter average cycle durations, and thus less reliability. So, what can we take away from these results? Most importantly, we can note that certain kinematic methods can reliably structure these biomechanical waveforms in gait, comparable to the kinetic-based methods. Firstly, the foot position methods, identified by heel strike and toe off, respectively, before, as I pointed out in the plot before. These methods directly track the motion of the heel or toe in space. Because the foot position changes clearly at heel strike and toe off, they offer a consistent cue that matches well with the kinetic contact data. This makes them robust and field-friendly alternatives to the force-based methods. And then I also identified the max knee flexion method, which defines a cycle based on the moment the knee bends the most. This isn't a traditional event like heel strike, but it turns out to be a repeatable and stable landmark in walking, and also happen to lead to consistent cycle durations. The other methods, however, use segment velocity or acceleration or less distinct features which perform worse. Some of these methods might respond to small fluctuations in movement, leading to variable or inconsistent event timing. As a result, they structured cycles with durations that deviated significantly from the kinetic gold standard. So the key takeaway here is when choosing a method to structure gait, if not kinetic, we have to look at the feature that the method is using, consider how stable and repeatable that the feature is across different people and walking styles, and think about the analysis that you're doing. So for example, if you're calculating average joint angles over the cycle, inconsistent structuring could skew your results a lot. So that is why it is critical to test methods thoroughly before using them in large-scale studies or clinical analysis. With that, I'd like to thank you for listening.